Good afternoon, everybody. I'm glad to present our work at IEEE Big Data 2023. And this paper titled A Cascaded Spatial-Temporal Approach for Long-Lead Streamflow Forecasting. And I'm Ping, and this is joint work with Yong, David, Patrick, Wahid, and Shafiq, and Wei. Okay, so let's get started. So we all know flooding is actually a major problem, and especially as we have climate change. And the flooding, especially in the developing world, and 80% of the flood affected population, and it accounts for a majority of this flooding event and the impact. And one recent example is in Bangladesh, and so 80% of the population and the area actually is in low-lying floodplains. So it's a huge problem for many people, and the loss is significant. So there is an urgent need for more accurate and also long lead flood warning system. And I'm going to talk about why the long lead here is actually a big factor. For the challenges here, and so usually for the long lead forecasting, and the definition is usually at least 5 to 10 days, before, the flood prediction, and so we have enough time to prepare. But technically, and there are quite a few challenges. And the first one here is, of course, the low scale. And the model here often underestimates the rainfall and precipitation, and we know that's actually a problem. And this kind of underestimation will be more harmful than overestimation. And uncertainty is also high, and uncertainty, of course, comes from the data collection part, and for data mining people and the technical people here, and like us, actually, this kind of uncertainty comes from due to the chaotic nature of the weather systems, right? And we now all know in a chaos system, and if your starting condition and also this boundary condition change a little bit, and the outcome will change significantly. So that's due to the challenge of a chaos system. And data collection part, as I said, is actually a huge challenge if you want to collect enough data. And so all of this actually will make significant challenges for this kind of long lead, we call it a long lead, and also accurate flood prediction. And traditionally, of course, there are a lot of models and work that will try to deal with these problems. And I list a few here. And from the early models like ARMA and ARIMA until more like hydrological models, and from the hydrological community. And recently, of course, our data-based and also machine learning models here. And within the machine learning models, we have RNN, we have LSTM, and GRU that will deal with these temporal correlations in the data, right? Especially in the time series data. And also there are CNN models, and these are used to deal with the spatial features from this kind of forecasting. And in our approach, actually, we try to combine these two, and we developed a model called Castle. And now let's get started to take a look. And first, we give a definition for a spatial temporal event chain. And as you can see here, we try to combine the features from spatial and also temporal domains. So spatial-temporal event chain, or we call it stack, is an ordered series of spatially related events that occur sequentially over time. So we try to, again, take into consideration of both spatial and temporal features. And from the picture, and you can see here, and along the axle, and this is our temporal chain here, and over time, and we need to consider at least 3 kinds of features or category of features, and like rainfall and runoff and this flow increment. So rainfall, of course, is the first event, right? We start with rainfall, and then this rain fall into ground, and then we have this runoff, and then we need to calculate or measure the flow increment, and then eventually there will be flood or not, right? So that's our prediction. Okay, and for a more formal formulation, and as I said, there are 3 steps, and so as you can see, we try to measure, well, at the time t, right? And what will be the outcome, or that will be amount of flood, and for this 3-step stack, right? Spatial-temporal event chain. Okay, so at time t, we want to know the previous p days or p time steps, right? And for the rainfall, and because this will, of course, impact the runoff and the flow increment. So we take into consideration the previous p days or p time steps. And F here, we use it to represent the runoff, and so that means, again, taking into consideration the previous p days and what will be the runoff at time t. And finally, the flow increment, and again, we take into consideration of p previous days and what will be the flow increment, right? Again, at time t. Okay, and so after we calculate and figure out the R and Z and the flow increment, and we have the QT here, so this will be the actual stream flow at the forecast location at time t, right? So because our flood forecasting, of course, you need pinpoint a location, right? You are interested in, and you want to actually forecast, right? So usually that will be, it could be an area with some dense population, right? So that's of your interest, and to protect the lives and the property. Okay, and so for this Q here, and as you can see, we formulate it as a function of Q t minus s, and also the function of fq, right? So that will be the current flow here, and also plus the increment. So it will be the current actual flow total. Okay, so with this formulation here, and of course we want to optimize our actual prediction, and we try to fusion together all of this information from this temporal sequence and also spatial sequence, and try to fuse these 2 categories of features together, and to give a good prediction of lead time Q. So that's what we try to do. Okay, so here is our model. So as you can see here, it's a kind of complex model, and because we try to take into consideration of both our temporal and also spatial features. So again, along the in the middle, you can see the time axis here, and what we try to do is along the time, and we take into consideration of p days. So that's the history data we have, right? And then we try to predict the q days. So that's actually what we want to achieve, right? Like next day, the next 2 days, next 3 days, and the next q days, and we try to predict, what kind of stream flow and whether it will lead to, flooding or not. And along the vertical axis here, and you can see we actually put this spatial data into work, and so we try to look at the three features like the runoff and the rainfall and street flow, and over again a geographical area of area here, and that will affect the location you try to predict. And so for this one here, and we use the CNN models, and because the CNN models, as you can see, it can basically summarize your spatial features and find the correlations among different areas and how they will affect each other. And this can be both 3D and or 2D, depending on the data you have. Okay, but the key here is will be this convolutional blocks, and they will change along the time, and we use GRU to find these correlations along this temporal time series of data. Okay, so eventually we will put them together into these fully connected layers, and to take advantage or consider both categories of features, and then give a prediction here over time, and what will be the stream flow amount, and so that will be the basis for flooding prediction. Okay, so let's look at some data, right? Because this kind of model and is pretty practical, right? And also the flooding, problem we are working on is also a very, very real world problem. So we use some real world data, right, to try to predict. And the data we use is from Harding Bridge, and that's from the Gans River, and we know that's a big river. And we use data from 1985, 2002, 2016, and the picture or the area map is shown here. So you can see this is basically from the geological community, and they did a lot of work, right? And also this hydrological community here, and they figure out which area, which streams, and which basin, and will actually affect our prediction location. Okay, so we have some settings, and you can take a look at the paper, and you can see we pick the P and the observation days, and also the forecasting, and also the stream flow, and as the hyperparameter here. And again, this mainly from our hydrological collaborator and from their domain knowledge. And we try to compare with some competitive models. And this is our EQ-SIM, and a very traditional and strong model. And here is a comparison. And we try to measure it with multiple metrics like MAE, IMSE, and R-square. And so you can see our model here. And we used 2D data and 3D data. So that will be on the last two columns, Castle 2D and Castle 3D. And the Castle 2D here performs well, and the Castle 3D, of course, performs better, right? We have more data, and it shows our model, the Castle model here, really takes advantage of this data and find, quite, the correlations quite well, and gave 5-day prediction, 7-day prediction, and even 10-day prediction. And so give the best performance. And so we also did some ablation study, and so with these different models like the regular AN model and RIMA model and CN, RN, LSTM models here, and to compare. And here is a chart here to show how they work here. And so again, the Castle model here, the full Castle model here, and performs, gives the best performance. Okay, so here is our conclusion. And so first we give a formulation of the Streamflow forecasting and for flooding, and we consider both temporal and spatial features. And the model here, as you can see, it consists of GRU, for temporal features, and also convolutional blocks, the CN part, and for the spatial features. And we compare with different existing models and show the effectiveness of our approach. And also we conducted some ablation study, and to show if you don't consider spatial features or if you don't consider temporal features, and we will lose some performance. Okay, so this will be our last slide here, and I'm sorry I cannot really come to present in person, but if you get any questions, you are welcome to contact any of these authors. Okay, so thank you.